Tonight, we're going to talk about something that sounds like pure science fiction, but is actually being seriously discussed by physicists right now: traveling faster than light. For over a century, we've been told this is impossible. Einstein's equations, the foundation of modern physics, set an absolute speed limit on the universe. Nothing can travel faster than light. Not rockets, not particles, not information, not anything. It's one of the most fundamental laws we know. And yet, hidden within those same equations, physicists have discovered something extraordinary. A theoretical loophole that doesn't break the speed limit, but makes it irrelevant. By the end of tonight, you're going to understand how this works, why it's both revolutionary and deeply problematic, and why humanity's ability to reach the stars depends on solving problems we barely understand. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the problem. The universe is staggeringly, incomprehensibly large. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. That means light, traveling at 186,000 miles per second, takes over 4 years to make the journey. If we sent a spacecraft there using our current fastest technology, it would take tens of thousands of years to arrive. The observable universe stretches 93 billion light-years across. These distances are so vast, they defy human comprehension. And if we're limited to traveling slower than light, then the universe is effectively unreachable. We're confined to our tiny corner of space, prisoners of distance and time. This isn't just disappointing from an exploration standpoint. It has profound implications for the future of humanity. If faster-than-light travel is impossible, then we can never visit other star systems in any meaningful way. We can't colonize distant worlds. We can't meet other civilizations if they exist. We're stuck here, isolated by the cosmic speed limit, on one small planet orbiting one ordinary star. But here's where it gets interesting. Einstein's theory doesn't actually say that nothing can move faster than light. What it says is that nothing can move through space faster than light. And that distinction, subtle as it sounds, changes everything. Let me explain. When Einstein developed special relativity in 1905, he discovered that the speed of light is constant. It's always the same, 186,000 miles per second, no matter how fast you're moving or how fast the light source is moving. This seems impossible at first. If you're on a train moving at 100 miles per hour and you throw a ball forward at 20 miles per hour, someone standing still sees the ball moving at 120 miles per hour. The speeds add up. That's intuitive. That's what we expect. But Einstein showed that light doesn't work this way. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, the light doesn't move at 1.5 times the speed of light from the perspective of someone watching you. It moves at exactly the speed of light. The same speed, always. For every observer, this seems to violate common sense. How can light be moving at the same speed for both you and someone watching you when you're already moving at half-light speed? Einstein's answer was radical. Space and time adjust to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the perspective of someone standing still. And distances in the direction you're moving actually contract. They shrink. These aren't illusions. They're real, physical effects. Time dilation and length contraction are fundamental properties of the universe. We've measured them countless times in particle accelerators, atomic clocks on airplanes, GPS satellites orbiting Earth. They're real. And they get more extreme as you approach the speed of light. If you could travel at 99% of light speed, time would run 7 times slower for you compared to someone at rest. At 99.9%, it would run 22 times slower. At 99.99%, 70 times slower. And as you approach light speed, time dilation approaches infinity. From your perspective on the ship, the journey might take years. But from the perspective of someone on Earth, centuries or millennia might pass. But here's the critical part. As you go faster, your mass effectively increases from the perspective of someone watching you. The energy required to accelerate you further increases too. And as you approach the speed of light, the energy required approaches infinity. You would need infinite energy to reach light speed, which is impossible. This is the barrier. This is why nothing can accelerate to light speed through normal means. The laws of physics prevent it. The closer you get, the harder it becomes, until finally, you simply cannot push any harder. Light itself can travel at light speed because photons have no mass. But anything with mass, anything made of atoms, anything physical, cannot reach that speed. It's a fundamental limit built into the fabric of reality. And for over a century, this seemed like the final word on the matter. Faster than light travel was impossible. Physicists accepted it. Science fiction writers ignored it or invented fictional technologies to work around it. Warp drives, hyperspace, wormholes, all the classic tricks, but none of it was real. None of it was based on actual physics. It's worth understanding just how final this seemed. This wasn't like other barriers that humans had broken through. This wasn't like the sound barrier, which was a real engineering challenge but not a fundamental limit. Chuck Yeager broke the sound barrier in 1947 by flying faster than sound waves could propagate through air. It required a specially designed aircraft and a lot of courage, but it was achievable because there was no law of physics preventing it. The sound barrier was an aerodynamic challenge, not a cosmic prohibition. But the light speed barrier is different. It's woven into the fundamental mathematics of spacetime itself. Every test, every experiment, every observation confirms it. Particle accelerators push protons to 99.9999% of light speed. That's fast enough that the protons circle the 16.8-mile ring of the Large Hadron Collider 11,000 times per second. And yet, no matter how much more energy you pump in, you can never quite reach 100%. The protons get closer and closer, but they never quite make it. It's like an asymptotic curve in mathematics, approaching a limit but never touching it. This has been tested billions of times. Every particle physics experiment confirms it. The speed limit is real. But here's where it gets interesting. The limit applies to objects moving through space. And space itself is not an object. Space is the stage on which objects move, the fabric of the universe itself. And Einstein's equations, the very equations that set the speed limit, also describe how space can bend, warp, expand, and contract. They describe gravity as the curvature of space. They predict that the universe is expanding, that space itself is stretching. And nowhere in those equations is there a limit on how fast space can expand. This is crucial. Let me say it again, because it's the key to everything that follows. Objects cannot move through space faster than light, but space itself can expand or contract at any rate. There's no speed limit on the expansion of space. We know this for certain because we observe it. The universe is expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they're receding. Galaxies that are far enough away are receding faster than light, not because they're traveling through space at that speed, but because the space between us and them is expanding. Imagine ants on the surface of a balloon. If you inflate the balloon, the ants don't move across the rubber surface, but they get farther apart because the surface itself is stretching. The ants aren't violating any speed limit. They're not moving at all, relative to the rubber beneath their feet. But from each ant's perspective, the other ants appear to be moving away because the space between them is growing. This is exactly what's happening with galaxies in our expanding universe. And the expansion rate can exceed the speed of light without violating relativity. In fact, during the first fraction of a second after the Big Bang, the universe underwent a period of inflation where space expanded exponentially. The universe grew from smaller than an atom to larger than a grapefruit in a tiny fraction of a second. The expansion rate during inflation was far, far faster than light, incomprehensibly faster. This isn't speculation. This is our best current understanding of cosmology, supported by observations of the cosmic microwave background, the large-scale structure of the universe, the distribution of matter. Inflation happened. Space expanded faster than light. The universe did it naturally. And if the universe can do it, maybe we can harness it. Until 1994. That year, a physicist named Miguel Alcubierre published a paper that changed everything. He was a graduate student at the time, working at the University of Wales. He had been watching Star Trek, specifically an episode featuring the Starship Enterprise traveling at warp speed. And he wondered, as any physicist might, whether such a thing could actually work. Not the fictional technobabble version, but a real, mathematically rigorous version based on Einstein's equations. So he sat down and worked through the mathematics. And to his surprise, he found something. A solution to Einstein's field equations that described exactly what he was looking for. A way to move faster than light without actually moving through space at all. He published a paper titled The Warp Drive, Hyper-Fast Travel Within General Relativity. And it's one of the most remarkable ideas in modern physics. Here's how it works. And I want to be precise about this, because the details matter. Alcubierre realized that while you can't move through space faster than light, space itself has no such restriction. Space can expand and contract at any speed. We know this because the universe itself is expanding. Distant galaxies are moving away from us faster than light, not because they're traveling through space faster than light, but because the space between us and them is expanding. The galaxies aren't moving. Space is stretching. And there's no limit on how fast space can expand. It's not a thing moving through space. It's space itself changing. Einstein's equations allow this. In fact, they predict it. They describe a dynamic space-time that can warp and bend and change shape. So Alcubierre asked a simple but profound question. If space can expand and contract naturally, could we engineer a situation where we control that expansion and contraction? Could we create a bubble of space-time around a spacecraft? Could we compress space in front of the ship, making the distance shorter, and expand space behind it, making that distance longer? The ship would then surf on this wave of contracting and expanding space. Think of it like a surfer on an ocean wave. The surfer isn't swimming forward. The water beneath the surfboard is pushing the surfer forward. The wave moves, carrying the surfer with it. Similarly, the Alcubierre drive would create a wave in space-time that carries the spacecraft. From the ship's perspective, from the reference frame of someone on board, the ship isn't moving at all. It's sitting perfectly still inside a bubble of normal, flat space-time. No acceleration, no forces, no time dilation. The passengers would experience normal time, normal space, normal physics. They could walk around, eat lunch, have conversations, completely unaware that anything unusual is happening. But from an outside perspective, from someone watching from Earth or another stationary reference frame, the ship appears to be traveling faster than light. It's moving across space at speeds that would normally be impossible. Except it's not really moving. The space around it is moving. The ship is being carried by the motion of space-time itself. It's like you're standing on a moving walkway at an airport. You're not walking, you're standing still, but you're covering distance because the walkway is moving beneath your feet. That's the Alcubierre drive. You compress space ahead of you and expand it behind you, and you ride that wave across the universe. And here's the beautiful, elegant part that makes this more than just science fiction. Nothing in Einstein's equations forbids this. The math works. Alcubierre wrote down the exact metric, the precise mathematical description of how space-time would have to be shaped to create this effect. You can plug it into the field equations of general relativity and verify that it's a valid solution. It satisfies all the requirements. It doesn't violate the speed of light limit, because nothing is moving through space faster than light. The ship is stationary in its own reference frame. Space is doing all the work. You're not breaking the law. You're using a loophole, a feature of general relativity that allows space to move at any speed. It's like the difference between walking across a room and having the room move around you. Same result. Completely different mechanism. And because you're not actually accelerating, you don't experience time dilation. You don't age slower than people back on Earth. You arrive at your destination having experienced the same amount of time as someone watching from a distance. This solves one of the major problems with conventional, faster-than-light travel. If you could somehow accelerate to faster-than-light speeds through normal means, time dilation effects would be catastrophic. The faster you go, the slower time runs for you. At light speed, time stops completely from your perspective. Go faster, and you'd theoretically be traveling backward in time, creating paradoxes. But the Alcubierre drive avoids this entirely. You're not moving through space, so no time dilation. When Alcubierre published this idea in 1994, it caused a sensation in the physics community. Physicists were stunned. Here was a serious proposal, published in a peer-reviewed journal, showing that faster-than-light travel might actually be possible. Not with rockets or engines that push you through space, but by manipulating space-time itself. The warp drive, the staple of science fiction for decades, suddenly had a mathematical foundation. It wasn't just fantasy anymore. It was physics. Speculative, theoretical, at the very edge of what's possible, but physics nonetheless. Conferences were held. Papers were written. Physicists around the world started examining the Alcubierre metric, checking the math, looking for flaws, and for a brief moment, it seemed like the universe had opened up. Like humanity's future among the stars was no longer a distant dream, but a real possibility. Alcubierre had shown that the equations allowed it. And if the equations allowed it, maybe it could be built. Maybe some future civilization, with enough knowledge and technology, could actually construct a warp drive and travel to the stars. But then, physicists started looking at the details. And that's when the problems emerged. Big problems. Fundamental problems that might make the Alcubierre drive forever impossible in practice, even though it works on paper. The first problem is energy. To create the Alcubierre drive, to warp spacetime around your ship in the way the equations describe, you need energy. A lot of energy. More energy than you can possibly imagine. How much? Alcubierre's original calculations, done carefully using the mathematics of general relativity, suggested you would need negative energy equivalent to the mass of the entire observable universe. Let me be very clear about what this means. The observable universe contains about 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star is a massive ball of plasma, fusing hydrogen into helium, releasing enormous amounts of energy. Our Sun, a fairly typical star, has a mass of about 2 times 10 to the 30 kilograms. That's a 2, followed by 30 zeros. In pounds, that's about 4.4 times 10 to the 30 pounds. The entire Milky Way galaxy contains about 1.5 trillion solar masses of material. That's stars, planets, gas clouds, dark matter, everything. And there are 2 trillion galaxies in the observable universe, each with hundreds of billions of stars. When you add it all up, the total mass energy of the observable universe is approximately 10 to the 53 kilograms. That's 10, followed by 53 zeros. In more comprehensible terms, that's about 100,000 billion kilograms. It's a number so large, it loses all meaning. Our brains simply aren't equipped to grasp quantities like this. And Alcubierre's calculations said you would need energy equivalent to all of that mass. Every atom, in every star, in every galaxy, in the entire observable universe. Converted into energy through Einstein's famous equation E equals mc squared. And not just any energy, negative energy. We'll get to what that means in a moment. But first, just sit with the absurdity of the energy requirement. You would need to harvest the entire universe to power a single spacecraft. To travel to one nearby star, you would need energy equivalent to all the stars in existence. This is obviously impossible. There isn't enough energy in the universe to power a device that requires the energy equivalent of the universe itself. It's a logical contradiction. It's like saying you need to empty the ocean to fill a swimming pool. The numbers don't work. Read that again. The mass energy equivalent of every star, every planet, every particle of matter in the observable universe, concentrated and converted into negative energy. Just to move one small spacecraft. This is obviously impossible. There isn't enough energy in the universe to power a device that requires the energy equivalent of the universe itself. It's a logical contradiction. But physicists didn't give up. Over the years, they refined the mathematics. They realized that Alcubierre's original design wasn't optimized. The shape of the warp bubble, the way it compressed and expanded space, could be modified. There were degrees of freedom in the mathematics, parameters that could be adjusted. Different bubble geometries required different amounts of energy. So physicists started exploring the mathematical space of possible warp drive configurations. They asked, what's the most efficient shape? What configuration requires the least energy? Can we reduce the energy requirements to something more reasonable? and they found ways to improve the design. In 1999, Chris van den Broek published a paper showing that by modifying the internal geometry of the bubble, you could reduce the energy requirements dramatically. His design used a bubble that was very small on the outside, but very large on the inside, like a TARDIS from Doctor Who. From the outside, the warp bubble would be tiny, maybe a few meters across, but the interior space would be much larger, big enough to contain a spacecraft. This modification reduced the energy requirement by many orders of magnitude. Instead of the mass of the universe, maybe you only need the mass of Jupiter. Jupiter has a mass of about 1.9 times 10 to the 27 kilograms. That's still enormous, about 318 times the mass of Earth, but it's far less than the mass of the entire universe. It's a number we can at least write down without running out of zeros. Still absurd, but better, much better. Then, in 2012, Harold White at NASA's Eagle Works laboratory published calculations suggesting further optimizations. By changing the thickness of the warp bubble wall, making it thinner and more focused, you could reduce the energy requirements even more. White's calculations suggested you might only need the mass energy equivalent of about 700 kilograms. That's roughly the mass of a small car. Suddenly, the warp drive went from requiring the mass of the universe to requiring the mass of a car. That's a reduction of something like 10 to the 50 orders of magnitude. It's one of the most dramatic improvements in theoretical physics, and it made the Alcubierre drive seem almost plausible. If you only need 700 kilograms worth of energy, that's still a lot, more than we can currently produce, but it's at least conceivable. We can imagine a future technology that could generate that much energy. A fusion reactor, perhaps, or matter-antimatter annihilation. 700 kilograms of matter converted entirely to energy, through E equals mc squared, would yield about 6 times 10 to the 19 joules. That's roughly the energy output of a large nuclear weapon. Enormous, yes, but not universe scale, enormous. It's within the realm of imaginable future technology. So for a while, it seemed like maybe, just maybe, the Alcubierre drive was back on the table. Maybe the energy requirements could be brought down to a level where some advanced civilization could actually build one. But there were problems with White's calculations. Other physicists examined his assumptions and found issues. The optimizations he proposed required very specific geometric configurations that might not be physically realizable. And even if they were, there was still the bigger problem: negative energy. The Alcubierre drive doesn't just need energy, it needs negative energy. And that's where things get really strange, really quantum, really uncertain. In everyday life, in the world we experience directly, energy is always positive. A battery stores positive energy that can do work, power a device, light a bulb. The sun radiates positive energy that warms the earth and drives photosynthesis. When you burn fuel in a car engine, you release positive energy that moves the vehicle. When you eat food, your body extracts positive energy to power your muscles and brain. Energy, as we understand it in daily life, is always positive. It's always something you can harness, something you can use, something that increases when you add heat or motion or electromagnetic fields. Negative energy sounds like science fiction. It sounds like antimatter or dark energy or some other exotic concept that doesn't exist in the real world. It sounds like something made up to make the math work. But it's actually real, or at least It's theoretically real according to quantum mechanics. And we have experimental evidence that it exists, at least in tiny amounts, under very specific conditions. There's something called the Casimir effect, predicted in 1948 by Dutch physicist Hendrik Casimir. Here's how it works, and this is one of the strangest predictions in all of quantum mechanics. If you take two uncharged metal plates, perfectly parallel, and place them extremely close together in a vacuum, they experience a tiny attractive force pushing them together. This isn't magnetism. The plates aren't charged. This isn't gravity. The masses are too small. This is something else entirely. Something quantum. The vacuum, the empty space between the plates, isn't actually empty. This is one of the profound insights of quantum mechanics. What we call empty space, a perfect vacuum with no particles, no air, no nothing, is actually seething with activity at the quantum level. Virtual particles, particle-antiparticle pairs, are constantly popping into existence and immediately annihilating each other. An electron and a positron appear out of nowhere, exist for a tiny fraction of a second, and then collide and vanish. A photon appears and disappears. Quarks flash in and out of existence. This happens everywhere, all the time, throughout all of space. It's called quantum fluctuation, and it's a direct consequence of the Heisenberg uncertainty principle. The uncertainty principle says you cannot know both the energy of a system and the time duration with perfect precision simultaneously. The more precisely you know one, the less precisely you can know the other. This means that over very short time intervals, energy can fluctuate wildly. Particle pairs can borrow energy from the vacuum, exist briefly, and then pay it back by annihilating. As long as they do this quickly enough, within the time limit set by the uncertainty principle, it's allowed. The vacuum is not empty. It's a roiling foam of virtual particles, a quantum field that's never quite at zero energy. And this quantum foam has energy. Specifically, it has 0-point energy, the minimum energy that a quantum field can have. Even at absolute zero temperature, even in a perfect vacuum, the quantum fields have this irreducible background energy. Now, here's where the Casimir effect comes in. When you place two metal plates close together, you restrict which virtual particles can exist between them. The plates are barriers. Only virtual particles with wavelengths that fit exactly between the plates can appear. Think of it like a guitar string. A guitar string can only vibrate at certain frequencies, wavelengths that fit exactly between the two ends where the string is fixed. You can have a wave that goes up and down once across the length of the string, or twice, or 3 times. But you can't have a wavelength that's 1.5 times the length of the string. It doesn't fit. Similarly, between the Casimir plates, only certain wavelengths of virtual particles can exist. Wavelengths that don't fit are excluded. But outside the plates, in the open space beyond, all wavelengths can exist. There's no restriction. So you have more quantum fluctuations, more virtual particles, more 0-point energy pushing on the outside of the plates than on the inside. This creates an imbalance, a pressure difference. And the plates are pushed together by this difference. The force is tiny, incredibly tiny, measured in nanonewtons for plates micrometers apart. But it's real. It's been measured in laboratories many times since the effect was first detected in 1958. The most precise measurements were done in 1997 by Steve Lamoureux, who measured the force between plates in a vacuum and found it matched the theoretical predictions almost perfectly. And here's the key point. The energy density between the plates is negative. It's less than the energy of empty space outside the plates. You've created a region where the energy is lower than zero, lower than the baseline quantum fluctuations of the vacuum. Negative energy. It exists. We've created it, measured it, confirmed it. This was stunning when it was first understood. Negative energy isn't just a theoretical curiosity. It's real. So the Alcubierre drive's requirement for negative energy isn't as crazy as it first sounds. Negative energy exists. We know how to make it. Problem solved, right? Not even close. The problem is scale. The Casimir effect produces incredibly tiny amounts of negative energy. We're talking about forces measured in billionths of a Newton, between plates separated by distances measured in millionths of a meter. The energy density is negative, yes, but it's minuscule. To power an Alcubierre drive, even with the optimized versions that require far less energy than the original proposal, you would need negative energy densities millions or billions of times greater than anything we've ever produced. You would need to create vast regions of space with enormous negative energy density, and you'd need to shape these regions precisely, forming them into the exact geometric configuration required by the Alcubierre metric. You'd need a bubble of normal space inside, surrounded by a shell of negative energy space, with the right thickness, the right curvature, the right energy density. And this bubble would need to be stable, maintained over the entire journey, potentially years or decades, for a trip to another star. We have no idea how to do that, not even theoretically. The Casimir effect is a laboratory phenomenon. You need carefully prepared metal plates in a precisely controlled vacuum. You need to eliminate thermal fluctuations, vibrations, any disturbance that could mask the tiny Casimir force. And even then, you're producing negative energy in a region micrometers thick between two plates. Scaling this up to a bubble, feet or miles across, with energy densities billions of times higher, maintained in open space, without plates or confinement, is so far beyond our capabilities that it might as well be magic. It's the difference between rubbing two sticks together to make a tiny spark and building a fusion reactor that produces the power of the sun. Technically, the same underlying physics, fire in one case and nuclear fusion in the other, but vastly different in scale and complexity. Some physicists have proposed using electromagnetic fields to enhance the Casimir effect. If you could create standing waves of electromagnetic radiation in just the right configuration, maybe you could amplify the negative energy production. Others have suggested using quantum fields, manipulating the vacuum state directly through exotic techniques we don't yet understand. But all of this is purely speculative. We don't have the technology. We don't even have the theoretical framework to know if it's possible. We can write equations that describe what would need to happen, but we can't say whether those equations correspond to anything that can actually exist in the real universe. And that's not even the worst problem. The worst problem is causality, the structure of cause and effect itself, and whether faster than light travel by any means might fundamentally break it. Here's what that means. And this is subtle but crucial. If you can travel faster than light, even if you do it by warping space rather than moving through it, you can potentially create paradoxes. Time travel paradoxes. Violations of causality, where effects precede their causes. Let me explain how this works, because it's not immediately obvious. Einstein's relativity tells us that there's no universal now, no cosmic clock ticking at the same rate everywhere in the universe. Different observers moving at different speeds disagree about what events are simultaneous. If you're on a spaceship, moving very fast relative to Earth. An event that happens now on Earth, from your perspective, might happen in the past or future, from the perspective of someone on Earth. This is called the relativity of simultaneity, and it's been confirmed by countless experiments. When you're moving at everyday speeds, the differences are tiny, unmeasurable. But as you approach the speed of light, the differences become significant. Events that you see as simultaneous, happening at the same time, are not simultaneous in other reference frames. This isn't a problem, as long as everyone is moving slower than light, because even though different observers disagree about the timing of distant events, they all agree on the causal order. If event A causes event B, everyone agrees that A happened first. The signal from A, traveling at or below light speed, arrives at B, and then B happens. The order is preserved. Causality is safe. But introduce faster than light travel, and this breaks down. Here's a thought experiment to show how. Imagine you have a spaceship with an Alcubierre drive. You travel from Earth to a star system 10 light-years away at 10 times the speed of light. From your perspective on the ship, the journey takes 1 year. You leave Earth in the year 2100, let's say, and you arrive at the destination star in 2101. Simple enough. But now consider the perspective of someone on Earth who's moving relative to your ship's reference frame. Because of the relativity of simultaneity, from their perspective, events at the destination star that you consider to be in the future are actually happening now or even in the past. If you then travel back to Earth using the Alcubierre drive, again at 10 times light speed, you could potentially arrive back at Earth before you left. Not from your own perspective. From your perspective, you spent a year traveling there and a year traveling back, 2 years total. But, from the perspective of certain observers, from certain reference frames, you completed a round-trip journey and arrived back before you departed. You could meet yourself before you left. You could prevent yourself from leaving in the first place. This is the grandfather paradox, the classic time travel problem. If you go back in time and prevent your grandfather from meeting your grandmother, you're never born. But if you're never born, you never go back in time. So your grandfather does meet your grandmother. So you are born. So you do go back in time and prevent them from meeting. It's a logical loop with no resolution, a contradiction that cannot be resolved within the laws of logic, and physicists hate this kind of thing. The universe appears to be fundamentally logical. Causes precede effect. Events follow from other events in a consistent, deterministic way, at least at the macroscopic level. Even in quantum mechanics, where things are probabilistic and weird, there are rules. Probabilities add up to 1. Information is conserved. The math is consistent. But time travel paradoxes break this. They create situations where logic itself fails, where you have contradictions that cannot be resolved. And most physicists believe the universe doesn't allow this. There must be some rule, some law, some mechanism that prevents these paradoxes from occurring. One of those mechanisms might be that faster than light travel, by any means, is fundamentally impossible. Not because of engineering challenges, not because we lack the energy or the technology or the clever ideas, but because allowing it would break causality and create paradoxes. The universe might simply not permit it. This is where things get philosophical and profound. Some physicists argue that any method of faster-than-light travel, no matter how clever, will always run into this problem. The Alcubierre drive, wormholes, quantum tunneling, any theoretical shortcut through spacetime. They all potentially allow time travel into the past, under the right conditions, in the right reference frames. And if the universe forbids time travel paradoxes, it must also forbid faster-than-light travel. The two are linked. You can't have one without the other. There's a principle in physics called the chronology protection conjecture, proposed by Stephen Hawking in 1992. It's not a proven theorem, not a law in the way Newton's laws or the laws of thermodynamics are laws. It's a conjecture, an educated guess based on the behavior of physics in extreme situations. Hawking's conjecture states that the laws of physics prevent time travel into the past, and therefore prevent any scenario that could lead to causality paradoxes. He called it chronology protection, because the universe appears to protect the chronological order of events, ensuring that causes always precede effects. We don't know if this conjecture is true. We don't have a proof. We don't have a complete theory of quantum gravity that would let us calculate what happens in these extreme scenarios. But there are hints, suggestive pieces of evidence that point in this direction. Every time physicists try to create a theoretical model that allows time travel, something goes wrong. Energy requirements become infinite. Singularities form points where the curvature of spacetime becomes infinite and the equations break down. Quantum effects destroy the structure, creating instabilities that prevent the time machine from forming. The mathematics develops pathologies, infinities, and divergences that suggest the solution isn't physically realizable. It's as if the universe is conspiring to prevent these things from happening. Every route you try, every theoretical path, ends up blocked, not by one barrier, but by multiple barriers, all working together to ensure that time travel remains impossible. And the Alcubierre drive might be the same. It works, on paper. The equations allow it. You can write down the metric, plug it into Einstein's field equations, and verify that it's a valid solution to the equations. But when you dig deeper, when you ask whether this solution can actually be realized in the physical universe, you find barrier after barrier. Energy requirements that started at the mass of the universe and have been reduced but are still enormous. Negative energy that we can barely produce in microscopic amounts in laboratories. Stability issues where the bubble might collapse or develop singularities. And causality violations that could break the logical structure of the universe itself. Each barrier might seem like an engineering challenge, something we could overcome with enough knowledge and technology and time. But taken together, they start to look less like challenges and more like fundamental prohibitions. Like the universe is telling us, through multiple independent mechanisms, this far and no farther. You cannot break the speed limit, not because of one specific law, but because the entire structure of space-time, causality, energy, quantum mechanics, all of it works together to prevent it. It's a conspiracy of physics, a coordinated effort by the laws of nature to protect the cosmic speed limit. And this conspiracy might be fundamental. It might not be something you can overcome with better technology. It might be written into the deepest laws of reality, the foundation on which everything else is built. But we can't be certain. And that uncertainty, that sliver of doubt, is what keeps physicists working on these ideas. Because there's always the possibility that we're missing something. That there's a deeper level of physics we haven't discovered yet. That our current theories, as successful as they are not the final word. And yet, physicists haven't given up entirely on the possibility of faster-than-light travel. Because there are other ideas, other theoretical approaches that don't rely on the Alcubierre drive. Other ways to achieve faster-than-light travel, or at least to achieve the effective result, the practical outcome of crossing vast distances quickly. Wormholes, for instance. These are one of the most famous concepts in theoretical physics, popularized by science fiction, but actually grounded in real mathematics. A wormhole is a hypothetical tunnel through spacetime, connecting two distant points in the universe. Think of spacetime as a sheet of paper. Normally, to travel from one point on the paper to another, you move across the surface, following the shortest path, a straight line, in this two-dimensional analogy. But what if you could fold the paper, bringing the 2 points close together, and then poke a hole through, creating a tunnel? You could step through the tunnel and instantly arrive at the distant point without traveling across the surface at all. That's a wormhole, a shortcut through spacetime. Instead of traveling the long way around through normal space, covering light years of distance at sublight speeds, you take a shortcut through the wormhole. From the perspective of someone watching you from normal space, it would look like you teleported. You disappeared from one location and instantly appeared at another location light years away. No journey, no travel time, just instantaneous transfer. But from your perspective, from your experience, you just walked through a tunnel. You entered one end, moved through a short passageway, and emerged at the other end. You didn't travel faster than light through space. You never exceeded the cosmic speed limit. You took a different route, a shortcut that bypassed most of the distance. And here's the remarkable thing. Einstein's equations actually allow wormholes to exist. They're not forbidden by general relativity. In fact, they're predicted as valid solutions to the field equations of general relativity, the same equations that describe gravity, black holes, the expansion of the universe. The first wormhole solution was discovered in 1916 by Carl Schwarzschild, the same physicist who derived the solution describing non-rotating black holes. Later, in 1935, Einstein himself, working with Nathan Rosen, described what's now called an Einstein-Rosen bridge, a theoretical wormhole connecting two regions of space-time. They didn't think of it as a tool for faster-than-light travel. They were exploring the mathematics of general relativity, finding all possible solutions to the equations. But the math was clear. Wormholes could exist. The equations allowed them. So, why haven't we found any? Why aren't we using wormholes to zip around the galaxy? Because there's a catch. Actually, several catches. The first is stability. Just like the Alcubierre drive, wormholes require negative energy to stay open, to remain stable and traversable. Without negative energy, a wormhole would collapse instantly, in far less than the time it would take for light to cross from one end to the other. The throat of the tunnel, the narrow passage connecting the two mouths, would pinch shut. Imagine trying to hold open a tunnel dug through loose sand without any supports. The walls would immediately collapse inward. A wormhole in normal space-time, without some form of exotic matter or negative energy to brace it open, behaves the same way. The immense curvature of space-time creates a kind of gravitational pressure that crushes the tunnel. To keep it open, you need something with negative energy density, something that pushes outward rather than pulling inward. You need the gravitational equivalent of a support beam, but made of exotic matter that has properties opposite to normal matter. And we're back to the same problem as the Alcubierre drive. We can create tiny amounts of negative energy in laboratories using the Casimir effect. But to stabilize a wormhole large enough for a spacecraft, or even large enough for a single atom, you would need vast amounts of negative energy, far more than we can produce. The energy requirements might be even worse than the Alcubierre drive. Some calculations suggest you would need negative energy equivalent to the mass of Jupiter distributed throughout the throat of the wormhole. Others suggest even more. And remember, this isn't ordinary energy that you can get from a power plant or a nuclear reactor. This is negative energy, exotic matter with properties we can barely create in the tiniest quantities under the most controlled conditions. Scaling it up to wormhole size is a problem we have no idea how to solve. There's also the question of creating a wormhole in the first place. Wormholes might exist naturally, formed in the intense gravitational conditions of the early universe or in the vicinity of black holes. But we've never observed one. We have no evidence that natural wormholes exist. Every black hole we've observed appears to be just that, a black hole, not a wormhole. The event horizon leads to a singularity, not to another region of space. At least, that's what our observations and theories suggest. So if natural wormholes don't exist, or are vanishingly rare, we would have to create one artificially. And here's the paradox. To build a wormhole connecting Earth to a distant star, you need two mouths, two openings, one here, one there. But to place the second mouth at the distant star, you first have to get it there. You have to transport one end of the wormhole across space to the destination, which means you have to travel there, the slow way, at sublight speeds, taking thousands or millions of years. Only after you've completed that journey can you use the wormhole for instant travel. It defeats the purpose for the initial journey. You'd spend millennia transporting the wormhole mouth to another galaxy, and only then could you use it for quick trips back and forth. Unless, of course, the wormhole already exists naturally, or unless there's some way to create both mouths simultaneously at different locations, which seems even more difficult. Some physicists have proposed that if wormholes exist naturally in space, we might find one nearby, perhaps left over from the Big Bang or created by some exotic process. If we could locate such a wormhole, stabilize it with negative energy, and determine where the other end leads, we might be able to use it. But this is wildly speculative. We've never seen a wormhole. We don't know if they exist. We don't know how to look for them. They might have observable signatures, tiny gravitational lensing effects, or unusual light patterns, but distinguishing these from other astrophysical phenomena would be extremely difficult. And even if you could create and stabilize a wormhole, you would face the same causality problems as the Alcubierre drive. Depending on how the wormhole is structured and how it moves through space, it could potentially become a time machine. Here's how. If you have a wormhole with one mouth on Earth and one mouth on a distant star, and you accelerate one of the mouths to near light speed and then bring it back, time dilation effects would cause time to pass differently at the two mouths. The accelerated mouth would age less than the stationary mouth due to relativistic time dilation. This creates a time difference between the two ends of the wormhole. Step through from the younger mouth to the older mouth, and you travel forward in time. Step through from the older mouth to the younger mouth, and you travel backward in time. You could potentially use this to send messages to your own past, creating the same grandfather paradox problems. Could you send information back through the wormhole, telling yourself not to create the wormhole in the first place? What happens then? These paradoxes suggest that the universe might prevent wormholes from being used as time machines. Maybe quantum effects destroy any wormhole that threatens to become a time machine. Maybe the negative energy requirements become infinite precisely at the moment when time travel would become possible. Maybe there's a fundamental law we haven't discovered yet that prevents closed time-like curves, paths through space-time, that loop back to their own past. Stephen Hawking's chronology protection conjecture again. The universe protects causality, and one way it might do that is by preventing wormholes from being traversable or from being configured in ways that allow time travel. So wormholes, like the Alcubierre drive, are allowed by the equations of general relativity. The math works. They're not explicitly forbidden. But when you examine the details, when you ask what it would take to actually create and use one, you run into enormous barriers, negative energy requirements that might be impossible to meet. The chicken and egg problem of getting the second mouth to the destination, causality violations that could break the logical structure of time itself, and quantum effects that we don't fully understand, but which might destroy any wormhole before it becomes useful. So, wormholes, like the Alcubierre drive, exist in this strange space between possible and impossible, theoretically allowed, practically unreachable, and perhaps fundamentally forbidden by deeper laws we haven't fully discovered. Then there's another idea that's been gaining attention, particularly in popular science discussions, though it's often misunderstood: quantum entanglement. This is one of the strangest phenomena in all of quantum mechanics, so strange that it troubled Einstein for the rest of his life. It's a phenomenon where two particles become connected, linked in a fundamental way that persists regardless of how far apart they are. Here's how it works. When two particles interact in certain ways, they can become entangled. Their quantum states become correlated. If you measure a property of one particle, like its spin, you instantly know the corresponding property of the other particle, even if it's on the other side of the universe. The measurement of one particle appears to instantly affect the other. Einstein called this spooky action at a distance, and he hated it. It seemed to violate the principle that nothing can travel faster than light. If measuring one particle instantly affects another particle light years away, aren't you sending information faster than light? Isn't that exactly what relativity forbids? This bothered Einstein so much that he proposed it as evidence that quantum mechanics was incomplete, that there must be some hidden variables, some deeper level of reality we hadn't discovered yet. He published a famous paper in 1935 with colleagues Boris Podolsky and Nathan Rosen, known as the EPR paper after their initials. The paper described what's now called the EPR paradox, a thought experiment showing that quantum mechanics seemed to require either faster-than-light communication or hidden variables. Einstein believed hidden variables were the answer. He thought quantum mechanics was missing something, that particles had definite properties before measurement, we just didn't know what they were. But he was wrong. In 1964, physicist John Stuart Bell proved mathematically that no hidden variable theory could reproduce all the predictions of quantum mechanics. Bell derived a set of inequalities, mathematical relationships that must be satisfied if hidden variables exist and if no information travels faster than light. Then, over the following decades, experiments tested these Bell inequalities. The most famous were done by Alain Aspect in the early 1980s and have been repeated and refined many times since. The results were clear. The Bell inequalities are violated. Hidden variables don't exist, at least not in any simple local form. Quantum entanglement is real. When you measure one particle, the other particle's state really is affected instantaneously, regardless of the distance between them. This has been confirmed over and over. We've demonstrated entanglement between particles separated by hundreds of miles. China's Mishas satellite has created entanglement between particles over distances of more than 620 miles. The correlation is real. It's instant. So this must allow faster-than-light communication, right? If measuring one particle instantly affects another particle far away, can't you use that to send a message? The answer, frustratingly, maddeningly, is no. Quantum entanglement doesn't allow you to send information faster than light, and the reason is subtle but crucial. When you measure an entangled particle, you get a random result. You can't control what you measure. If you're measuring spin, you might get spin up or spin down, but which one you get is fundamentally random. You can't force the result. Now, when you measure your particle and get spin up, you instantly know that the other particle, when measured, will give spin down. The correlation is perfect. The instant you learn your result, you know what the other measurement will show. But here's the key. The other measurement hasn't happened yet. And when it does happen, the person doing that measurement gets a random result from their perspective. They measure spin down, but they don't know why. They don't know if it's because you measured spin up on your entangled partner. They don't know if you've even performed your measurement yet. To learn that their measurement was correlated with yours, they need you to tell them what you measured. And you have to send that information through normal channels: a phone call, a radio signal, a letter, something traveling at or below the speed of light. Only after they receive your classical information can they compare the results and see the correlation. The entanglement itself doesn't carry information. It creates a correlation, but that correlation is only visible when you compare results, and that comparison requires classical communication at light speed or slower. So you can't use entanglement to send a message faster than light. You can't encode information in the entanglement itself. The phenomenon is real. The correlation is instant, but it doesn't violate relativity because no information is transmitted. It's one of the deepest and most subtle features of quantum mechanics, and it's been the subject of countless papers and debates and philosophical discussions. Some people have speculated about using entanglement to teleport matter, inspired by the phenomenon called quantum teleportation. This is a real effect, demonstrated in laboratories, but it's not what science fiction calls teleportation. Here's what actually happens. If you have an entangled pair of particles, and you have a third particle whose quantum state you want to transfer, you can perform a special kind of measurement that destroys the state of the original particle, while instantaneously creating the same state in the entangled partner. The quantum information is teleported from one particle to another. But critically, you still need to send classical information about the measurement results from the sender to the receiver. Without that classical information, which travels at light speed, the receiver can't decode the teleported state. So, quantum teleportation doesn't teleport the actual particle. It teleports information about the particle's quantum state. And it still requires classical communication. So it doesn't give you faster than light information transfer. And it certainly doesn't give you faster than light travel. You can't teleport yourself, or even a single atom, from one location to another faster than light using quantum mechanics. The phenomenon is fascinating, useful for quantum computing and quantum cryptography, but it doesn't break the light speed barrier. Every route physicists explore, every clever idea, every theoretical loophole seems to hit the same fundamental walls: energy requirements that might be impossible to meet, exotic matter, and negative energy that exist only in microscopic amounts. Causality violations suggesting the universe won't allow it. And quantum mechanics, which seems to offer hints of instant connections across space, but which never quite delivers actual faster-than-light communication or travel. The universe guards its speed limit jealously, through multiple independent mechanisms, all working in concert to ensure that nothing exceeds light speed. And this raises a profound question. Is the speed of light limit truly fundamental? Is it written into the deepest laws of nature in a way that cannot be circumvented? Or is it just a practical limit, something that might be overcome with sufficient knowledge and technology? We don't know. And that uncertainty is both maddening and exhilarating. Because if the limit is truly fundamental, if it's woven into the very fabric of reality at a level deeper than space-time itself, then the universe really is unreachable in any practical sense. We really are stuck here in our solar system, or at best, able to colonize a few nearby stars over thousands of years of slow, patient expansion. The galaxy would remain mostly unexplored during any individual civilization's lifetime. Other galaxies would be forever beyond our reach, visible but untouchable. We could photograph them, study them with telescopes, detect signals from them if any civilizations there are broadcasting, but we could never visit them, never send a probe, never make contact. The cosmos would be full of wonders we can see but never touch, places we can observe but never experience directly. It's a profoundly lonely picture of the universe. Every intelligent species, isolated on their home world or confined to their local stellar neighborhood. A bubble, perhaps a few dozen light-years across at most. Looking up at the same stars we do, wondering the same questions we wonder, but forever unable to reach each other, because the distances are simply too vast and the speed limit too strict. The universe would be like a vast archipelago where each island is occupied. Each one has its own civilization, its own history, its own discoveries. But the ocean between islands is simply too wide to cross. You can see the other islands on the horizon. You know they're there. You might even be able to signal to them with light. But you can never visit them, never shake hands with the inhabitants, never share a meal or walk their streets, or see their world with your own eyes. You're stuck on your own island for the entire duration of your civilization's existence, from the first primitive tool to the last fading star. Every discovery, every achievement, every work of art or scientific breakthrough happens in isolation. And when your civilization ends, whether through natural disaster or the death of your star billions of years from now, no one will ever know you existed. Your signals will travel outward at light speed, taking millions or billions of years to reach other civilizations. And by the time they arrive, you might be long gone. But if the limit is not fundamental, if there's a way around it that we just haven't discovered yet, if the warp drive, or wormholes, or some other method we haven't even imagined is actually possible, then everything changes. Everything. The galaxy becomes accessible, not just theoretically, but practically. Stars that seem impossibly distant, that would take tens of thousands of years to reach with conventional rockets, become destinations you could visit in your lifetime. Other galaxies, entire island universes containing hundreds of billions of stars, become places you could actually travel to, explore, map, study up close. The future of intelligence in the universe is not one of isolation, but of connection, communication, exchange, cooperation, and perhaps even conflict. Civilizations could meet face to face. You could shake hands with an alien, walk the streets of their cities, see their art, hear their music, taste their food, learn their history. They could visit Earth, see our oceans and mountains, experience our cultures, share our knowledge. Ideas could flow between civilizations, accelerating progress exponentially. A mathematical breakthrough on one world could benefit every world. A medical discovery could save lives across dozens of civilizations. Artistic movements could spread and evolve, influenced by perspectives that are genuinely alien, utterly different from anything humanity could produce alone. You could build something far greater than any single civilization could build alone. A network of inhabited worlds, linked by faster-than-light travel, cooperating on projects of galactic scale. Megastructures that span solar systems. Experiments that use the resources of entire star clusters. Observatories that coordinate across thousands of light years to achieve resolution impossible for any single telescope. The pooled knowledge of hundreds or thousands of civilizations, each bringing their unique perspective, their unique discoveries, their unique approach to understanding the universe. It would transform not just the physical possibilities, but the intellectual and cultural landscape. We would no longer be alone in our questions. We would have partners in the search for understanding, other minds wrestling with the same fundamental mysteries. What is consciousness? Where did the universe come from? Is there a deeper level of reality beneath quantum mechanics? These questions wouldn't be humanity's burden alone. They would be shared questions, pursued by countless civilizations, each bringing their own insights. The cosmos could be alive, with travel and communication and commerce and cultural exchange. A network of inhabited worlds, connected by warp drives or wormholes or whatever method, makes faster-than-light travel possible. Ships crossing the galaxy in weeks or months instead of millennia. Messages exchanged in real time instead of waiting centuries for a light-speed signal to arrive. A young person could decide to visit another galaxy, board a ship, make the journey, spend years exploring, and return home to their friends and family who had aged the same amount. The universe wouldn't be a static collection of isolated dots, but a dynamic, connected, living thing. Which scenario is correct? Which universe do we actually live in? The isolated one or the connected one? Right now, based on everything we know, based on a century of testing and observation and theoretical work, the evidence suggests the pessimistic view. The evidence suggests that faster-than-light travel is fundamentally impossible, not just difficult. Every theoretical path to faster-than-light travel runs into seemingly insurmountable problems. And there are good theoretical reasons to think these problems aren't just engineering challenges, but fundamental prohibitions. The universe appears to be structured in a way that forbids certain things, not through arbitrary rules, but through the logical consequences of how reality is built. Black holes have event horizons you cannot escape from once you cross them. Not because there's a physical barrier or wall at the event horizon. There's nothing there you can touch or see or measure. But because once you cross it, the geometry of space-time itself has changed. All future directed paths, every possible trajectory you could take, every path through space and time that moves forward rather than backward, points toward the singularity at the center. You cannot escape because escape would require moving backward in time, which is forbidden. The structure of space-time itself traps you. The second law of thermodynamics says entropy always increases in closed systems. Disorder always grows. You cannot unscramble an egg, cannot reassemble a shattered glass, cannot reverse the mixing of cream into coffee. Not because there's a law prohibiting it, but because the number of disordered states vastly outnumbers the number of ordered states. It's not impossible in principle for all the air molecules in a room to spontaneously gather in one corner. The laws of physics allow it. But the probability is so astronomically small that it will never happen in the lifetime of the universe. Entropy increases not by decree, but by statistics. by the overwhelming likelihood of disorder over order. The Heisenberg uncertainty principle says you cannot simultaneously know a particle's position and momentum with perfect precision. The more accurately you measure one, the less accurately you can know the other. This isn't a limitation of our measuring instruments. It's not that we lack good enough microscopes or sensitive enough detectors. It's that particles genuinely don't have both properties simultaneously with definite values. At the quantum level, before measurement, a particle exists in a superposition of possible positions and possible momenta. Only when you measure does it collapse into a definite state. And which state it collapses into is fundamentally random, governed by probabilities, but not determined. The uncertainty isn't a measurement problem. It's a fundamental feature of reality at the quantum scale. These aren't limitations of our technology or knowledge. They're fundamental features of how the universe works, constraints that emerge from the deepest laws of physics. And the speed of light limit might be the same. A feature so deeply embedded in the structure of spacetime, causality, energy, and quantum mechanics that it cannot be overcome no matter how advanced you become, no matter how clever your methods. But here's the critical point. The reason we can't be absolutely certain: our current theories, successful as they are not complete. We know they're not complete because they contradict each other at the extremes, in situations where both gravity and quantum mechanics are important. General relativity describes gravity and spacetime beautifully, with extraordinary precision. It predicts black holes, and we've photographed them. It predicts gravitational waves, and we've detected them with LIGO and Virgo. It predicts the bending of light around massive objects, and we've measured it countless times. It predicts the expansion of the universe, and we observe it in every direction. It's one of the most successful theories in the history of science. But it breaks down at singularities, points where density and curvature become infinite. At the center of black holes, the equations predict infinite density, infinite curvature, infinite tidal forces. These infinities can't be physically real. They're a sign that the theory is reaching its limits, that it's no longer applicable. At the moment of the Big Bang, general relativity predicts that the entire universe was compressed into a point of infinite density. Again, an infinity that signals the theory has broken down. Quantum mechanics, on the other hand, describes the world of particles and atoms and fields with incredible accuracy. It predicts the energy levels of electrons in atoms, and the predictions match observations to 10 decimal places or more. It predicts the behavior of semiconductors, the properties of lasers, the functioning of transistors and computer chips. Every piece of electronics you use depends on quantum mechanics being precisely correct. It's the most precisely tested theory in all of science. The anomalous magnetic moment of the electron, a quantum mechanical prediction, has been verified experimentally to better than 1 part in a trillion. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. The theory is astonishingly accurate, but it doesn't include gravity. Quantum mechanics treats spacetime as a fixed background, a stage on which particles move. But general relativity says spacetime is dynamic, curved by mass and energy, constantly changing. When you try to combine the two, to create a quantum theory of gravity that describes what happens when gravitational fields are strong and quantum effects are important, the theories collide. The mathematics breaks down. You get infinities and divergences that can't be removed by the usual techniques that work for other quantum field theories. The theories are incompatible at a fundamental level. This is the problem of quantum gravity. arguably the biggest unsolved problem in theoretical physics. We need a theory that describes gravity at the quantum level, a theory that tells us what spacetime is made of at the smallest scales, at the Planck length of about 10 to the minus 35 meters. A theory that tells us what happens at the center of black holes, what happened at the moment of the Big Bang. A theory that unifies general relativity and quantum mechanics into a single consistent framework. And we don't have that theory yet. We're working on it. Brilliant physicists around the world are pursuing different approaches, different ideas about how to solve this problem. But we haven't solved it. And until we do, we can't make absolute statements about what is and isn't possible at the frontiers where both gravity and quantum mechanics matter. We have candidates for quantum gravity. String theory is probably the most famous, the most widely discussed. It proposes that the fundamental building blocks of reality are not point particles, not zero-dimensional dots, but tiny, one-dimensional strings of energy. These strings are incredibly small, about 10 to the minus 35 meters long, the Planck length. That's 20 orders of magnitude smaller than an atomic nucleus. We have no hope of observing them directly with any technology we can currently imagine. But the idea is that different vibrations of these strings, different modes of oscillation, correspond to different particles. One vibration pattern looks like an electron. Another looks like a quark. Another looks like a photon. And critically, another looks like a graviton, the hypothetical particle that carries the gravitational force. String theory naturally includes gravity without putting it in by hand. The equations predict the existence of gravitons as one of the necessary vibration modes. This is a remarkable achievement. In quantum field theory, you have to add gravity separately, and when you do, the math breaks down. But in string theory, gravity emerges naturally from the mathematics. It's built in. The theory also requires extra dimensions beyond the three of space and one of time that we experience directly. Depending on the version of string theory, it requires 9 or 10 spatial dimensions total. That sounds absurd. Where are these extra dimensions? Why don't we see them? The answer string theory gives is that the extra dimensions are compactified, curled up into tiny shapes so small we can't detect them. Imagine a garden hose viewed from far away. It looks one-dimensional, a line, but up close you see it has a second dimension curled around the length of the hose. An ant walking on the hose can move forward and backward along its length, but also around its circumference. Similarly, string theory suggests that every point in our three-dimensional space actually has extra dimensions curled up at each point, too small to detect. The geometry of these compactified dimensions, the precise shape they form, determines the properties of particles in our three-dimensional world. Different shapes give different particle properties, different masses, different charges, different forces. String theory has some remarkable properties that make it appealing as a candidate for quantum gravity. It's mathematically elegant and consistent. It solves certain theoretical problems that plague other approaches. It provides a framework that might eventually explain not just gravity, but all the forces and particles in a unified way. But it's also unproven, completely unproven. We have no experimental evidence for strings. We can't probe the tiny Planck scale where string effects would become apparent. The energies required to test string theory directly, to create strings or observe their vibrations, are far beyond anything we can achieve with particle accelerators. You would need energies comparable to those in the first moments after the Big Bang. We can't build a collider powerful enough. String theory also makes very few testable predictions. Most of its predictions involve phenomena at energy scales or distance scales we can't access. There might be thousands or millions of different ways to compactify the extra dimensions, each giving a different set of particle properties, and we don't know which one corresponds to our universe. So, string theory might be right. It might be the correct description of reality at the deepest level, the theory that finally unifies quantum mechanics and gravity. Or it might be completely wrong, an elegant mathematical structure that doesn't correspond to the actual universe we live in. We simply don't know yet. But here's why it's relevant to faster-than-light travel. If string theory is correct, or if some other theory of quantum gravity is correct, it might reveal new possibilities that our current incomplete theories don't predict. Maybe there are shortcuts through the extra dimensions that string theory requires. Maybe particles or spacecraft could move through higher dimensional space and emerge far away in our normal three-dimensional space without ever traveling faster than light through any single dimension. Think of it like this, and this is just an analogy to build intuition. Imagine you're a two-dimensional being living on the surface of a sphere, like a balloon. From your perspective, trapped on the two-dimensional surface, the only way to get from one point to another is to travel along the surface. If you want to reach the point directly opposite you on the sphere, the antipodal point, you have to travel halfway around the sphere. The shortest path along the surface is a great circle route, covering a distance equal to half the circumference. But if you could move through the third dimension, through the interior of the sphere, you could travel in a straight line directly through the volume to the opposite point. The distance would be far shorter, just the diameter of the sphere rather than half the circumference. For a sphere of radius r, the surface distance is pi r, but the straight line distance through the interior is just 2r. If r is large, the shortcut through the third dimension is significantly shorter. From the perspective of someone confined to the surface, someone who can only perceive 2 dimensions, it would look like you teleported. You disappeared from one point and instantly appeared at another point on the opposite side of the sphere. You didn't break the speed limit for motion along the surface. You didn't travel faster than light within the 2-dimensional space. You just took a shortcut through a dimension that the 2-dimensional beings can't access or perceive. Maybe our 3-dimensional space is similar. Maybe there are higher dimensions we can't perceive directly, dimensions that are real and physical, but compactified or hidden from our everyday experience. And maybe there are ways, in principle, to use those dimensions as shortcuts, to move through higher dimensional space in a way that appears as faster than light travel in our 3 dimensions, but isn't actually violating the speed limit in the full higher dimensional space. This is wild speculation. It requires string theory, or something like it, to be correct, which we don't know. It requires that the extra dimensions have the right properties, the right geometry, to allow this kind of travel. It requires technology so advanced we can't even begin to describe it. Technology that can manipulate higher dimensions that we can barely prove exist mathematically, let alone access physically. But the point is, there are theoretical possibilities we haven't fully explored because our current theories are incomplete. Loop quantum gravity is another candidate theory of quantum gravity, completely different in approach from string theory. Instead of proposing strings as fundamental objects, loop quantum gravity keeps the idea of particles and fields, but proposes that space and time themselves are not continuous. At the smallest scales, at the Planck scale, space-time has a granular structure. It's made of discrete quanta, tiny, indivisible units of space and time. Space is not infinitely divisible. If you zoom in far enough, you reach a fundamental limit where the concept of smaller distances stops making sense. It's like pixels on a screen. From far away, an image on a screen looks smooth and continuous. But zoom in, and you see it's made of discrete pixels. Below the pixel level, the idea of position within the image breaks down. Similarly, loop quantum gravity suggests that below the Planck scale, about 10 to the minus 35 meters and 10 to the minus 43 seconds, our usual concepts of distance and time break down. Spacetime is fundamentally granular, and at this level, space and time might be emergent properties arising from the interactions and relationships of these fundamental quantum units, not fundamental themselves. Loop quantum gravity has been successful in describing the interior of black holes without singularities. Instead of infinite density at the center, the theory predicts that quantum effects prevent the collapse from reaching a true singularity. The density becomes enormous but finite. Similarly, it offers a model of the Big Bang as a big bounce, a transition from a previous contracting phase of the universe to our current expanding phase. The equations don't blow up at the beginning of time. They describe a smooth, if extreme, transition. But like string theory, loop quantum gravity is unproven. We can't test it directly. We can't observe the Planck scale structure of space-time with any current or foreseeable technology. And we don't know yet whether it allows any loopholes for faster-than-light travel, any ways to exploit the quantum structure of space-time to travel faster than light. It might impose the same restrictions as our current theories. The quantized nature of space-time might make the speed limit even more rigid, more fundamental. Or it might reveal that at the Planck scale, the rules change in ways we haven't imagined, that new phenomena become possible. We don't know. The point is, our theories are incomplete. We know they're incomplete because they don't work together in extreme conditions, because they give nonsensical answers like infinities where there should be finite numbers, because there are questions they can't answer. And when you have incomplete theories, you cannot make absolute statements about what is impossible forever. You can say, what's impossible according to the theories you currently have. You can say faster-than-light travel is impossible according to general relativity and special relativity. But you can't rule out the possibility that a more complete theory, a theory of quantum gravity that successfully merges general relativity and quantum mechanics, will change the picture in unexpected ways. Physics is full of examples where new theories revealed possibilities the old theories couldn't predict. Before quantum mechanics, physicists thought atoms were the smallest units of matter, indivisible by definition. The word atom comes from the Greek atomos, meaning uncuttable. Quantum mechanics and particle physics revealed that atoms have internal structure. They're made of electrons orbiting a nucleus, and the nucleus is made of protons and neutrons, and those are made of quarks and gluons. The uncuttable was cut, again and again, revealing deeper layers of structure. Before relativity, physicists thought space and time were absolute, fixed, independent, the unchanging stage on which physics plays out. Newton's laws assumed a universal time that flows the same for everyone, everywhere. Relativity revealed that space and time are flexible, relative, intertwined into a single four-dimensional space-time that warps and bends. What seemed fixed turned out to be dynamic. Before we understood nuclear physics, before we knew about fusion, The sun was a profound mystery. How could it shine for billions of years without running out of fuel? No chemical process could provide that much energy. The best calculations suggested the sun should burn out in just thousands or millions of years, far too short for geology and biology, which indicated Earth was much older. The discovery of nuclear fusion solved the mystery completely. The sun wasn't burning chemically like a campfire. It was fusing hydrogen nuclei into helium, releasing energy through the conversion of mass to energy via E equals mc squared. Suddenly, the timescales made sense. The sun has enough hydrogen fuel to shine for about 10 billion years total, and it's about halfway through that lifetime. The impossible became possible when we discovered new physics. So sometimes, the seemingly impossible becomes possible when we discover deeper layers of reality, when we develop theories that go beyond what we currently understand. And maybe faster than light travel is the same. Maybe we're missing something crucial, some piece of physics that will change the picture entirely when we finally discover it. Or maybe not. Maybe the barriers are real and fundamental, written into the deepest laws of reality in a way that no new physics can overcome. Maybe the universe really does forbid faster than light travel absolutely, through mechanisms so fundamental they cannot be circumvented. We're at the edge of our knowledge, standing at a boundary we can perceive but not yet cross. Looking out into the unknown, and we can't see clearly what lies ahead. We can't know with certainty whether the speed limit is absolutely fundamental or whether there's a loophole waiting to be discovered. The second law of thermodynamics says entropy always increases. You cannot unscramble an egg. The Heisenberg uncertainty principle says you cannot simultaneously know a particle's position and momentum with perfect precision. These aren't limitations of our technology. They're fundamental features of reality, and the speed of light limit might be the same. A fundamental feature that cannot be overcome, no matter how advanced you become, but we can't be certain. Physics is full of surprises. Things that seemed impossible turned out to be possible. Heavier than air flight was considered impossible by serious scientists until the Wright brothers did it. Splitting the atom was thought to be impossible until we did it. Going to the moon was science fiction until we did it. Sometimes the impossible just means we haven't figured it out yet. And sometimes new theories reveal possibilities the old theories missed. Newtonian physics said nothing could exceed the speed of light. Then Einstein came along and showed that the speed of light was actually constant and nothing with mass could reach it. But he also showed that space and time were flexible, that gravity was the curvature of space-time, that the universe was far stranger than Newton imagined. Maybe there's another revolution coming. Maybe there's a deeper theory, a theory of quantum gravity that unifies general relativity and quantum mechanics that will reveal new possibilities. Some physicists think string theory might provide answers. String theory suggests that the fundamental building blocks of reality are not point particles, but tiny vibrating strings of energy. Different vibrations correspond to different particles. And string theory requires extra dimensions beyond the three of space and one of time that we experience. Maybe there are shortcuts through these extra dimensions. Maybe particles or spacecraft could move through higher dimensional space and emerge far away in our normal space without ever traveling faster than light through any dimension. This is wild speculation. String theory is still unproven. We have no experimental evidence for it. It's mathematically elegant, and it solves certain theoretical problems, but it might be completely wrong. And even if it's right, there's no guarantee it allows faster than light travel. Loop quantum gravity, another candidate theory of quantum gravity, also suggests that space and time are not continuous, but are made of discrete units, quanta of space and time at the smallest scales. Maybe at these scales, the rules change. Maybe new phenomena become possible. But again, this is speculation. We don't have a confirmed theory of quantum gravity yet. We're still working on it. And until we do, we can't say for certain what is and isn't possible. What we can say is this. Based on our current understanding, faster-than-light travel appears to be impossible. Not because we lack the technology, though we certainly do, but because the laws of physics seem to forbid it. The Alcubierre drive works on paper, but requires exotic matter and enormous energy and might create causality paradoxes. Wormholes are theoretically possible, but face the same problems. Quantum entanglement doesn't allow information or matter to travel faster than light. Every route we explore hits a wall. And those walls might be fundamental. But the universe is under no obligation to make sense to us. It's under no obligation to be easily understandable or to reveal all its secrets. We're still learning. We're still discovering. And there are hints, tantalizing hints, that there might be more to the story. One of those hints comes from the fact that the universe itself doesn't obey the speed limit. Space can expand faster than light. During the first fraction of a second after the Big Bang, the universe underwent a period called inflation, where space expanded exponentially, far faster than light. This is accepted cosmology. It's how we explain the uniformity of the cosmic microwave background and the large-scale structure of the universe. Inflation happened. Space expanded faster than light. If space can do this naturally, why couldn't we harness that process? Why couldn't we create a localized region of space that expands rapidly, carrying a spacecraft with it? That's exactly what the Alcubierre drive proposes to do. And, while we don't know how to create the necessary conditions, the fact that the universe itself did it suggests it's not fundamentally forbidden. Another hint comes from black holes. The interior of a black hole is one of the most extreme environments in the universe. Space and time switch roles inside the event horizon. The singularity at the center is not a place, but a moment in time, a point in the future that everything inside the black hole is doomed to reach. We don't understand what happens at the singularity because our equations break down there. General relativity predicts infinite curvature, infinite density, quantities that don't make physical sense. We need a theory of quantum gravity to describe what really happens. And that theory might reveal new physics. It might show that singularities don't actually exist, that something else happens instead. And maybe that something else involves structures or phenomena that could be harnessed for faster-than-light travel. This is extremely speculative. We're talking about physics we don't understand, happening in places we can never observe directly. But the point is, there are gaps in our knowledge, places where the current theories fail, and in those gaps, new possibilities might hide. We also have to consider the Fermi paradox, one of the most profound questions in all of science. The Fermi paradox is the apparent contradiction between the high probability that extraterrestrial civilizations should exist and the complete lack of evidence for them. The name comes from physicist Enrico Fermi, who during a lunch conversation in 1950 asked a simple question that has haunted astronomers ever since. Where is everybody? Let's think through the logic carefully. The galaxy is billions of years old, about 13.6 billion years to be precise. It contains somewhere between 200 billion and 400 billion stars, each one a potential sun for planets to orbit. We now know, thanks to missions like Kepler and TESS, that planets are common. Most stars have planets. Some stars have many planets. In our galaxy alone, there are probably hundreds of billions of planets. Many of those planets are in the habitable zone, the region around their star where liquid water could exist on the surface. We've already identified thousands of potentially habitable planets, and we've only surveyed a tiny fraction of the galaxy. On Earth, life emerged relatively quickly after the planet cooled enough to support it. Earth formed about 4.54 billion years ago. For the first few 100 million years, it was a hellish place, bombarded by asteroids, with a molten surface. But by about 3.8 billion years ago, maybe earlier, life had already appeared. That's less than 1 billion years after the planet formed. Life didn't wait. It emerged quickly, as soon as conditions allowed. This suggests that life, at least simple microbial life, might be easy to start. If the ingredients are present, water, organic molecules, energy sources, life seems to find a way. So if life emerges easily and planets are common, then the galaxy should be teeming with life. And if life is common, intelligence should have evolved many times. On Earth, it took about 3.5 billion years to go from simple cells to intelligent humans. That's a long time, but it happened. And there's no reason to think Earth is unique. The same evolutionary processes should work elsewhere. And if intelligence evolves, technology eventually follows. Humans went from stone tools to spacecraft in about 10,000 years. That's an eye blink in cosmic time. So, if intelligence is common, and if it leads to technology, then there should be technological civilizations all over the galaxy. And some of those civilizations should be far older than ours. Earth is about 4.54 billion years old. The oldest stars in the galaxy are over 13 billion years old. Planets could have formed around those stars 10 billion years ago. Life could have started 9 billion years ago. Intelligence could have evolved billions of years before humans appeared. A civilization that arose even 1 million years before us would have a 1 million year head start in technology. Imagine what humanity might achieve in 1 million years if we don't destroy ourselves. Now, imagine a civilization that's had a 1 billion year head start. What could they build? What could they achieve? Even traveling slower than light, at 10% or 20% of light speed, using generation ships or self-replicating probes. A civilization could colonize the entire galaxy in just a few million years. The galaxy is about 100,000 light-years across. At 10% light speed, crossing it takes 1 million years. Add time for building colonies, launching new missions, and you might need 10 million years to fill the whole galaxy. That sounds like a long time, but it's nothing compared to the billions of years the galaxy has existed. If even one civilization arose 1 billion years ago and started expanding, they should be everywhere by now. We should see evidence of their technology, their constructions, their signals, megastructures harvesting the energy of stars, self-replicating probes exploring every star system, radio or optical signals carrying information across the galaxy, signs of astroengineering, of civilizations reshaping solar systems to suit their needs. Something, anything. And yet, we see nothing. We've listened for radio signals with programs like SETI, the search for extraterrestrial intelligence. We've scanned thousands of stars. We've looked for narrow band signals, the kind that only technology can produce. We've found nothing. Silence. We've looked for optical laser pulses, brief flashes that might be interstellar communication. Nothing. We've searched for signs of astroengineering, like Dyson spheres or partial Dyson swarms that might create unusual infrared signatures. We've found some interesting candidates, but nothing conclusive. We've looked for industrial pollution in the atmospheres of exoplanets, chemicals that might indicate technological activity. Nothing yet. The galaxy appears empty, or at least devoid of obvious technological civilizations. This is the Fermi paradox. Where is everybody? There are many proposed solutions, and none of them are entirely satisfying. Maybe life is rare. Maybe the emergence of life requires such specific conditions, such a precise sequence of events, that it only happens once in a galaxy or once in a universe. Earth might be a fluke, an incredibly unlikely accident that can't be repeated. But this seems improbable, given how quickly life appeared on Earth and how robust it's been since. Maybe intelligence is rare. Maybe the step from simple life to intelligent, technological life is incredibly difficult. It took 3.5 billion years on Earth. Maybe most planets with life never make that leap. Maybe we're the exception. Maybe civilizations destroy themselves. Maybe every technological civilization eventually develops weapons powerful enough to annihilate itself, and eventually does so. Nuclear weapons, bioweapons, artificial intelligence, nanotechnology. There are many ways a civilization could end itself. Maybe the window between developing technology and destroying yourself is so short that civilizations don't last long enough to colonize the galaxy. This is a depressing solution, and it has implications for our own future. Maybe they're deliberately hiding. Maybe advanced civilizations exist but choose to remain quiet, to avoid revealing themselves. Maybe they fear other civilizations, or maybe there's a galactic code of conduct, a rule that you don't interfere with younger civilizations. The zoo hypothesis suggests Earth is a nature preserve, watched but not contacted. But this requires every civilization in the galaxy to agree and comply, which seems unlikely. But there's another possibility that's directly relevant to our discussion tonight. Maybe they can't travel faster than light, either. Maybe the speed limit really is fundamental, absolutely insurmountable, and that's why the galaxy isn't full of spacefaring civilizations. If faster-than-light travel is impossible, then colonizing the galaxy becomes much harder. You can still do it with generation ships, but it requires a level of commitment and stability that most civilizations might never achieve. You're sending ships on journeys lasting thousands or tens of thousands of years. The people who arrive are descendants of the people who left, hundreds of generations removed. It requires maintaining technology and social cohesion across time spans longer than recorded human history. Most civilizations might try and fail, might lose interest, might collapse before completing the colonization. And even if you succeed, you're still stuck in your local region of the galaxy. The civilizations are scattered, isolated, unable to maintain real-time communication or travel between star systems. Each colony world develops independently, potentially diverging from the others over thousands or millions of years. There's no galactic empire, no united civilization, just isolated pockets separated by distances that take decades or centuries to cross, even for light-speed signals. If this is true, then the universe really is full of isolated civilizations, each developing alone in their own corner of the galaxy, each one looking up at the stars and wondering if anyone else is out there. each one seeing the same empty sky we see. It's a lonely picture of the universe, but it might be accurate. It might be that the speed of light limit is so fundamental, so strictly enforced, that it prevents galactic-scale civilizations from forming. Or maybe the opposite is true. Maybe faster than light travel is possible, but it requires physics or technology so advanced, so difficult to discover, that most civilizations never figure it out. Maybe it requires understanding quantum gravity. Maybe it requires resources or energy sources we can't imagine. Maybe it requires a level of cooperation and long-term planning that most civilizations never achieve. Maybe 1 in a million civilizations breaks through and discovers how to travel faster than light. Maybe those civilizations are out there, traveling the galaxy, meeting each other, building something extraordinary. But they're so rare, or so careful, or so far beyond us, that we haven't encountered them yet. Maybe we're on the cusp of joining them. Maybe in 100 years or 1,000 years, we'll solve the puzzle and the galaxy will open up to us. Or maybe we never will. Maybe we're destined to remain here, looking up at the stars, wondering forever. We don't know which scenario is correct. And that uncertainty, that not knowing, is perhaps the most frustrating part of all. We're at the edge of our understanding. We have theories that work brilliantly within their domain, but break down at the extremes. We have tantalizing hints that faster-than-light travel might be possible, but every path we explore seems blocked. And we can't know for certain until we push further, until we develop a deeper understanding of space-time and quantum mechanics and how they fit together. So, where does this leave us? It leaves us with a choice. We can accept the speed limit as fundamental and focus on what's achievable. We can develop better propulsion systems, systems that can accelerate us to a significant fraction of light speed. 10% of light speed, 20%, maybe, with enough advancement, 50%. At those speeds, the nearest stars become reachable within a human lifetime. Proxima Centauri, at 20% of light speed, would take about 21 years. That's a long journey, but it's doable. We could send generation ships, spacecraft designed to support multiple generations of humans during the journey. The people who arrive would not be the people who left, but their descendants. We could send slower probes, robots that don't need life support, that can travel for centuries and send back data. We could use suspended animation if we ever develop the technology, putting astronauts in a state of hibernation for the journey. These are all within the realm of possibility. They don't require new physics. They require engineering, determination, resources, but they're achievable in principle. And maybe that's enough. Maybe exploring the nearest few dozen stars over thousands of years, building a slow network of human outposts across nearby space, is a worthy goal. Or we can keep searching for the loophole. We can keep investigating the Alcubierre drive, refining the mathematics, looking for ways to reduce the energy requirements, searching for methods to create and stabilize negative energy. We can study wormholes, both theoretically and observationally, looking for evidence that they exist naturally or for clues about how to create them. We can pursue a theory of quantum gravity, hoping it will reveal new possibilities that our current theories miss. This is a longer shot. It might not pay off. We might spend centuries researching these ideas only to conclude definitively that they don't work, that the universe really does forbid faster than light travel. But the potential reward is enormous. If we succeed, if we find a way to break the light barrier or circumvent it, then the entire galaxy opens up. Stars that would take thousands of years to reach conventionally become accessible in years, or months, or even days. The whole character of spaceflight changes. We go from being a species confined to one star system to a species that can explore the galaxy. That's worth pursuing. Even if the odds are long, even if the challenges seem insurmountable, the possibility alone is worth the effort. And maybe we'll discover something unexpected along the way. That's how science works. You investigate a question, and you find an answer you weren't expecting. You develop a technology for one purpose, and it enables something completely different. The physicists working on these problems today aren't naive. They know the obstacles. They know that faster-than-light travel might be impossible. But they also know that the only way to find out for certain is to push the boundaries, to explore the edges of theory, to ask the hard questions. And even if faster-than-light travel turns out to be impossible, the research won't be wasted. Studying the Alcubierre drive teaches us about general relativity, about the structure of space-time, about the limits of our theories. Investigating negative energy deepens our understanding of quantum mechanics and the vacuum. Pursuing quantum gravity could revolutionize physics, even if it doesn't give us a warp drive. The journey itself has value, regardless of the destination. So, let's come back to where we started. The idea that you could travel faster than light. For a century, this was considered impossible. Einstein's equations set an absolute speed limit. Then physicists discovered theoretical loopholes, ways to manipulate spacetime that don't violate the laws as written, but achieve the same result. The Alcubierre drive, wormholes, shortcuts through higher dimensions. Each of these is grounded in real physics, derived from equations we know work. They're not fantasy. They're speculative, theoretical, at the very edge of what might be possible. But they exist on paper. The math allows them. And yet, every attempt to make them work in practice reveals deeper problems. Energy requirements that might be impossible to meet. Exotic matter that might not exist in the quantities needed. Causality paradoxes that suggest the universe fundamentally forbids these scenarios. The universe appears to guard its speed limit through layers of constraints. It's not just one barrier. It's barrier after barrier, each one more difficult to overcome. And this might be the universe's way of saying no. Not through a single law, but through a conspiracy of laws, all working together to ensure that nothing, no matter how clever, can truly exceed the speed of light. Or maybe we just haven't figured it out yet. Maybe there's a path through the barriers that we haven't found. Maybe a future civilization, with knowledge and technology we can't imagine, will look back at our attempts and smile at how close we came. We don't know. And that uncertainty is both frustrating and exciting. It means the question is still open. The universe hasn't given us a final answer. We're still exploring, still discovering, still pushing the boundaries of what's possible. And maybe that's the most important thing. Not whether faster-than-light travel is ultimately achievable, but that we're asking the question, that we're not content to accept limits without testing them, that we look at the universe, vast and distant and seemingly unreachable, and we ask, how can we get there? That drive, that curiosity, that refusal to accept impossibility without proof is what makes us human. It's what took us from caves to cities, from the ground to the moon, from isolated tribes to a global civilization. And it's what will take us to the stars, one way or another. Whether we do it slowly, over thousands of years, at a fraction of light speed, building generation ships and outposts, and gradually expanding across nearby space. Or whether we find the loophole, the trick, the theoretical breakthrough that lets us warp space and leap across light years in the blink of an eye. Either way, we're going. The question is just how long it takes and how far we can reach. So the next time you look up at the night sky and see the stars scattered across the darkness, remember this. Those stars are distant, impossibly distant, separated from us by light years of empty space. The nearest one would take over 4 years to reach, even if you could travel at light speed, which you can't. According to everything we know, the speed of light is a limit you cannot exceed. But hidden in the same equations that set that limit are hints, suggestions, mathematical curiosities that say, maybe, just maybe, there's a way around it. We don't know if those hints are real. We don't know if the loopholes will hold up under scrutiny. We don't know if the barriers can be overcome, or if they're fundamental prohibitions written into the fabric of reality. But we're looking. We're calculating. We're testing the boundaries. And one day, maybe in our lifetimes, maybe in the next century, maybe far in the future, we'll know. We'll know if the stars are forever out of reach, or if the universe has one more secret to reveal. One more impossible thing that turns out to be possible after all. Thank you for joining me on this journey to the edge of physics and possibility. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the cosmos and the questions that define our place in it. And remember, the universe is full of mysteries. Some we've solved, some we're still working on, and some we haven't even thought to ask yet. The speed of light might be a limit, or it might be a challenge. Good night, and may your journeys, wherever they take you, always push the boundaries of what's possible.